So, this is Ishan and me, Akshay's presentation on the A-star algorithm, obviously a graph algorithm that we did not learn in class. And so just for a quick overview of it, so A-star is a efficient shortest path graph searching algorithm, and so its speed comes from the fact that it is essentially a implementation of the Dijkstra's algorithm with a heuristic added onto it. And so this speed, the extra speed from A star comes from the fact that it utilizes a heuristic, which of course means sacrificing some of its accuracy for that extra speed. And so just to preface, a heuristic is a part of like a software component where you in essence, like what I just said, sacrifice some of your accuracy for a better computation time, for better speed. And so as I talk later on about like the components in the A-star algorithm, you'll see how like some of them aren't the exact value but are simply approximations of it. So that's where like the heuristic comes in. And so now just looking at a component and some of the algorithm components, we first have an open list which stores the nodes that need to be evaluated, the ones that have not been explored yet by the A-star algorithm. And opposite to that, we have a closed list which holds nodes that have already been evaluated. And then we have our three subfunctions, which all play a part in calculating like the total cost of a node, which is what we judge like the node on when we're like choosing which node to move to next. And so first we have G or G of n, which is the cost to get from the starting point or starting node to the current node n, or to a given node n. And then we have H of n, which is the approximate cost to get from node n to the goal or like the ending node that you want to get to. And so notice how I said this is the approximate cost versus the value in G of n is the actual cost, is the accurate cost. Because of course, in order to get like the actual cost to get from the node n to the goal, we have to trace the path from the goal to every single node in the tree, which is very computationally expensive. So what we do is that we use different functions, different like heuristic models to approximate the cost. So I'm pretty sure the one that we have implemented is a Euclidean formula or like the distance formula. So that's just one example. There's many others like that. And so finally, we have f of n, which is just the sum of the two previous functions, g of n, h of n. And so this is in a sense the actual cost of a vertex or like not vertex, but a node that we use to like judge it on to see where we're going to go next. And so then finally we have a search tree, which is what we update as we like keep going through the algorithm as we like search a tree. And so this is just to like keep track of all the nodes that you have searched, like figuring out like how they are in relation to each other. And it helps a lot when you're tracking, when you've reached the end goal and you have a shortest path, tracing out the shortest path. This is how we do it, is that we just use the search tree for that, as I'll explain now. So let's go through here like a typical like search process. So first we add the starting node to the open list, and we add such that its cost is just the approximate value from the starting node to the, or from the current node to the goal, because of course the g in this case will be 0 since the cost to go from the starting node to the starting node is 0. And now we move into the more general like loop of the algorithm, which is to select a node n from the with the lowest cost or f from the open list. We move that node n from the open list to a closed list, and then now for each neighbor of n, we calculate their respective costs or their respective f or f of k. And so if node k is not in the open list, we add to the open list. If node k is in the open list, then we update its cost value or its f of k value with like the smaller value if it's found, which in this case just means like if we found a shorter path, that's basically what we're doing, updating it. And so next, we add the node k to our search tree under its respective parent, just to keep track of everything. And then we repeat steps 2 to 7 until the goal node is reached and explored, or until the open list is empty and we've reached no goal node. We haven't reached the goal node. And so we can see like there's like this specific requirement of having the goal node explored in addition to it being reached is important, because we might encounter the goal node in our first like run through of the graph, but that doesn't necessarily mean that that path is the shortest path. There might be others in there, which is why the goal node has to be explored as well to ensure that there's no other shortest path. And so after the step, if the open list is empty, then there's no path to the goal node because we weren't able to reach the goal node and we have no other nodes to search. If the goal node is reached, then we use the search tree that we made to reconstruct the shortest path using the parent pointers. So this just means going from the bottom of the tree, the leaf node, all the way to the top, all the way to the top to the root, which just replicates going from the goal node to the starting node. And so now I'll hand it off to Ishan to talk more about the implementation of this algorithm, the A-star algorithm.
Now let's take a look at our pseudocode. Our first step is to initialize an open and closed list. Our open list is initialized as a min heap, and our closed list is initialized as a queue. We're going to start by putting the start node into the open list. We're then going to loop through a certain set of code while the open list is not empty. So we're going to end this loop essentially when the open list is empty. Next, we're going to get the current node, and the current node is going to be the node with the lowest f value in the open list. And since we're doing this over and over again, it's useful to have the open list set up as a min heap. Once we've found the target goal, we're going to backtrack to get the total path, and we're going to do whatever code we need to do that. So if that means that we want to print out the values, then we're going to basically print out going backtracking in the closed list. Next, we're going to generate the children, which means that we're going to let the children of the current node equal the adjacent nodes, and then we're going to have another loop. This loop is going to loop through all the children in the list of children that the current node has. Next, we're going to check if the child is in the closed list, which means that we've already explored the node already. If we have, then we're going to skip the rest of the code in this loop and go to the next child. If we haven't, then we're going to compute the G, H, and F values for this child. If this child is already in the open list, then we're going to skip the we're not going to add the child to the open list. If it is not in the open list, then we're going to add the child to the open list. And then we're going to recurse, we're going to iterate over and over again until we find the optimal trajectory. So a couple of applications of the A-star algorithm is, first off, in robotics. We can use this to plan our paths, create autonomous robots, and create warehouse automation. The second application is in navigation. We can have GPS routing applications like Google Maps, Waze, and Apple Maps that make routing more efficient for our daily users. The third application is logistics and delivery. Supply chain delivery softwares speed up the transportation of these packages. For example, UPS and DHL certainly use algorithms like A-star to speed up their delivery process. And finally, network routing is a huge application. If we have a series of network communication devices, then we want to figure out the optimal path of how we can communicate from point A to point B. When looking at our runtime analysis, we looked at a couple different articles, and we found that the best analysis was with the branching factor and the depth. Note, this is very different from what we learned in class, because what we learned in class is with V and E, which is number of vertices and number of edges. However, we didn't find any analyses online for the A-star algorithm that used this, because most of the applications involved a very high or even infinite V value, number of vertices. So using the B branching factor, which is the average number of children per parent, and the depth D, which is the depth of the optimal solution, we can develop a worst case runtime of O of B to the D power. And then for the best case, we have O to the D, or O of D, sorry. This occurs when the heuristic perfectly guides the search to the goal. The worst case occurs when the heuristic function is non-informative and useless. So then the algorithm has to end up searching through every single node. So as you can see here, the key determinant of the performance is actually this heuristic function.